Hello hi, it's Mr. Neil here. In this video we're going to look at the data representation topic from the Computer Systems Unit within Higher Computing Science. With regards to data representation, you're required to be able to describe and exemplify the use of binary to represent both positive and negative integers. You need to be able to convert 2's complement numbers from binary to decimal and vice versa. You also need to be able to describe and exemplify floating point representation of both positive and negative numbers using the terms mantissa and exponent. And we'll look at the relationship between the number of bits assigned to the mantissa and exponent and the range and position of floating point numbers. And then looking at how text is stored, we're going to discuss the advantages of Unicode over extended ASCII and look at the advantages and disadvantages of bitmap and vector graphics. So let's dive straight in. So firstly, a quick recap of how we convert positive integers, so positive whole numbers, from decimal to binary and from binary to decimal. So if you want, pause the video now and have a go at completing these two conversions. Let's start with the decimal to the binary conversion. We wanted to convert the number 173 into binary. So we ask ourselves, does 128 go into 173? The answer is yes, so we write a 1 down and then we write down the remainder, in this case 45. And we ask ourselves again, does 64 go into 45? No, it doesn't, so we carry the 45. 32 does go in, and it gives us 13. 16 doesn't go into 13, so we write a 0 and carry it. 8 does go in, so we write a 1, carry the 5. 4 does go in, leaving us 1. 2 doesn't go into 1, so we then have 1010, 1101 as the binary equivalent of 173. Now for this binary number here, 0101, 1100. To convert it to decimal, we make a note of where all the ones are, and then we simply add them up. So 0101, 1100 in decimal is 92. When we're storing negative numbers, or negative whole numbers specifically, we use a method of representation called 2's complement. And there are 3 steps to convert a negative decimal whole number to a 2's complement binary number. These 3 steps are, firstly, we find the positive value. So in an example, we're looking to find negative 166 in binary. We start by finding the binary number for 166, which is 01111010. We then switch the 1s and the 0s, and that means any 0 becomes a 1 and any 1 becomes a 0. And lastly, we add 1. Now the simplest way to add 1 is starting at our least significant bit, which is 1, and we keep moving up until we find a 0. And we're going to replace that 0 with a 1, and any numbers to the right of that become 0, as you can see here. So minus 166 in 2's complement binary is 10001100. Here's another example, negative 84. Why don't you have a go at working this out yourself? So in this example, we're looking to find the binary 2's complement number for minus 84. So our first step is to find the positive value for 84. So 128 into 84 doesn't work, so we put a 0. 64 into 84 works and leaves 20. 32 into 20 doesn't work, so we carry it. 16 into 20 works and leaves us 4. 8 into 4 doesn't work. 4 into 4 works, and therefore we have nothing left. So positive 84 in 8-bit binary is 010101000. Our next step is to flip the ones and the zeros. So this means any 0 becomes a 1 and any 1 becomes a 0. So if flipped, we now have 10101011. Our last step is to add 1. Essentially what you're looking to do is, starting at 1, find the first bit that has got a 0, put your 1 in there, and then anything to the right of that becomes 0. And then we write the rest of the number as it is, 10101. And there we have our answer. Negative 84 in 2's complement is 10101100. And here we have an exam question from the 2019 exam paper. Again, why don't you have a go at working this out yourself? Okay, let's have a look at how we convert minus 128 into 8-bit 2's complement. For the first step we're going to do is we're going to write out our binary heading, starting at 1 and going up until we have used 8 bits. Then you'll recall the first step is we need to find the value for a positive 120. So 128 does not go into 120. 64 does go into 120, leaving us 56. 32 does go into 56, leaving us 24. 16 does go into 24, leaving us 8. 8 does go into 8, and that leaves us with nothing. Our next step is to then flip the 1s and the 0s. So any 0 becomes a 1 and any 1 becomes a 0. And lastly, we then need to add 1. So we're going along, starting at 1, going along, and we're looking for the first bit that is a 0. We turn that into a 1, and then any bits to the right become a 0. And then we drop the rest of it down. So minus 120 in 8-bit 2's complement is 10001000. Now there may be times when you're given a binary number and asked to convert that binary number to decimal. Now if we're using 2's complement, the most significant bit, which is the one to the left hand side, will always be 1. So let's convert this from binary to decimal. The easiest way is we start with our placeholders: 1, 2, 4, 8, 16, 32, 64, and 128. But what we do to the most significant bit is we make it a negative. So therefore, negative 128, we add 8, and we add 4. And this will give us negative 116. Why don't you have a go at working out example 2? For example 2, we do the exact same thing. We place our placeholders in, we take the 128, and we turn it into a negative. In this case, negative 128 plus 64 plus 8 plus 2 plus 1 gives us negative 53. Now when we're storing negative integers, we need to think about the range of the numbers that we can store. So if we're using 8 bits, the lowest number that we can store is negative 128, and the highest number that we can store is positive 127. This means the overall range when using 2's complement is negative 2 to the power n to 2 to the n minus 1. Let's now move on to talk about real numbers. So real numbers are numbers with decimal points. To store real numbers, we use a system called floating point representation. The fraction part is called the mantissa, and the power part is called the exponent. You may have made the link between floating point representation and scientific notation. When we're storing real numbers using floating point representation, there are three parts to a number. The sign bit is a single bit, and it denotes whether the number is positive or negative. The mantissa is a positive binary fraction, and the exponent is the power of 2 stored using 2's complement notation, because the exponent can be negative or positive. Let's have a look at this example on the right hand side. The floating point number below, 01101011, utilises 4 bits for the mantissa, including the sign bit, and 3 bits for the exponent. So let's start by splitting up so we can see the sign bit, mantissa, and the exponent. When we determine the exponent, the decimal place is to the left hand side. Our sign bit here is 0, so our number is positive. Our mantissa is 0.1101. Our exponent, we need to work out the decimal equivalent. So 1 and 2 is 3. And because we're timesing 2 to the positive of 3, we move the numbers up 3 places and we get 110.1. In this example, you will notice that our sign bit is 1, which suggests to us that it is a negative number. So it is negative 0.1101. In our exponent, it's stored using 2's complement, and the first value is a 1. Therefore, it is a negative number. In this case, this value here is negative 4, and if we add negative 4 onto that, we get times 2 to the minus 3. And in this case, we now move our number down 3 places. So we get 0.00011101. Here we have an exam question from the specimen question paper. We have to convert the number 0.001001 to floating point representation. We have to use 16 bits from the mantissa, including the sign bit, and 8 bits for the exponent. If you wish, you can have a go at answering this question here now, or keep watching and I'll go through it with you. So firstly, I'm going to write out the number so that I've got space around it. So our sign bit is going to be a 0 because it is a positive number. To work out the mantissa, we're going to move the decimal point 1, 2 places. And because we're going to the right, it is negative 2. And our mantissa then becomes 10001. But we're told that we need 16 bits for the mantissa, including the sign bit. At the moment, our mantissa is 1, 2, 3, 4, 5 bits long. We need to make it 15. So in this case, we just add another 10 zeros. Now for our exponent. Our exponent has to be 8 bits. 1, 2, 4, 8, 16, 32, 64, 128. And we're looking for the positive value for 2, which will be 0, 0, 0, 0, 0, 0, 1, 0. We then flip the 1s and the 0s, so we get 1, 1, 1, 1, 1, 1, 0, 1. And lastly, we add 1, which becomes 1, 1, 1, 1, 1, 1, 1, 0. And there we have our answer. So this question is worth 3 marks. We get 1 mark for correctly identifying the sign bit, 1 mark for correctly identifying the mantissa, and 1 mark for correctly identifying the exponent. With floating point representation, we have to take into consideration as to the precision and the range of the numbers that we can store. The range is the distance from the lowest to the highest in a set of numbers. So for example, if I have 4 bits, I have a range from 0 to 15, and with 8 bits, a range from 0 to 255. The precision of a binary number is how accurately it can produce the original decimal number. Depending on the amount of storage set aside, data loss is possible. This would result in the binary number being less precise. The number of bits allocated to floating point representation is usually fixed. So if we have got 40 bits for storing a floating point number, then we could set aside 32 bits for the mantissa and leaving 8 bits for the exponent. The number of bits allocated to the mantissa affects the precision of the number, and the number of bits allocated to the exponent affects the range of the numbers that can be stored. Moving on now to talk about text and how text data is stored in binary. At National 5 we encountered extended ASCII. And extended ASCII uses 8 bits for each character, and that means it can represent 256 different characters. However, there are more than 256 different characters across all the languages in the world, and this is where Unicode comes in. Unicode uses 16 bits to represent each character. This means that Unicode can represent 65,536 different characters. And that accounts for the majority of all the languages in the world, including emojis. So by using 16 bits to represent a character, we have access to lots more storage and therefore lots of different characters. At National 5 we looked at bitmap and vector graphics, and this is really just a summary. A bitmap graphic stores the data by every single pixel in an image. This means that images can be very realistic, and we're able to identify and edit each individual pixel. And no matter the software that we use, the image will always look the same. However, as we know, if we zoom into the image, we will get pixelization. If we want to edit the image, we have to edit each individual pixel, advantage and a disadvantage. And because it's pixeled, it's difficult to convert to vector graphic format. And again, because we're storing the detail of every single pixel, the file sizes are going to be large. Whereas a vector graphic is a type of graphic that stores an image as a collection of objects, rectangles, ellipses, polygons, and many others. And we store the attributes of these objects, so the coordinates, the length of them, the breadth of them, the fill colour. This means because we're storing the attributes of these objects that we can make the images much larger and keep the quality. It also means I can edit individual objects within an image. It's easily converted to bitmap file formats, and because we're only storing the instructions of the image as opposed to the whole image itself, the file size is relatively small. A disadvantage, however, is it's difficult to create realistic images. I can't edit the whole image, only the individual objects. And depending on the hardware or the software that I'm using, there might be a slight difference in the appearance or quality. So in this video, I have covered the data representation part of the computer systems unit within higher computing science. We have looked at 2's complement for storing positive and negative integers. We've looked at floating point representation for storing positive and negative numbers. We've briefly touched upon Unicode, bitmap graphic and vector graphics.